Heavy-tailed self-regularization in deep neural networks. This is a re-recording of a talk I gave at the NeurIPS2023 workshop that we hosted on heavy tails in machine learning and AI. Who am I? Well, I did my PhD at the University of Chicago back in the 90s. I studied with Carl Fried. You may know one of my more famous classmates, John Jumper, who invented AlphaFold. I then did my postdoctoral work. I was an NSF postdoctoral fellow in theoretical chemistry at Champaign-Urbana in Klaus Schulten's group. And you may know another one of my classmates, Jürgen Schmidhuber, who apparently has invented everything else. Now, I've been working in industry for 20 years doing applied machine learning and AI. And today what I'd like to talk to you about is some research I started about 8 to 10 years ago with a friend of mine at UC Berkeley, Michael Mahoney, on implicit self-regularization in deep learning. This work is based on 3 key papers, although we do have probably a dozen papers in the field. The 3 being the first, our JMLR 2021 paper, Implicit Self-Regularization in Deep Neural Networks, Evidence from Random Matrix Theory and Implications for Learning. This is about a 50, 60-page paper which lays out some of the early ideas in our phenomenological model to explain heavy tails in deep neural networks. We had a follow-up paper predicting trends in the quality of state-of-the-art neural networks without access to training or test data. This paper was published in Nature Communications 2021. Finally, there's a follow-up paper I'm working on with Chris Hendricks and Michael Mahoney called Semi-Empirical Theory of Learning, and I'm going to talk about some of the key results from this work. Again, this is probably a 50 to 60-page paper, which is going to lay out the statistical mechanics theory behind what we're doing and also the Weight Watcher project. This is an invited submission to Philosophical Magazine, although we're still trying to finish it, and hopefully we'll have it done by the end of the year or next month. Please reach out to me if you'd like a preprint. What is the problem we're trying to solve? We would like to understand how the layers in a neural network converge. Now, most people who study neural networks study how the loss function changes. If you're fancy, you might study the Jacobian or the Hessian, but what we're interested in is how the individual layers converge, because we have an idea that different layers would converge at different rates for the data set. And then we'd like to know if some layers are underfit, that is, they don't actually capture as much information from the data set as they could. And we'd like to have a theory that would tell us when a layer is ideally fit to the data that it's being trained on. We also would like to understand whether certain layers are overfit, meaning that they've learned spurious correlations from the data, and therefore this might hurt their out-of-sample performance and or induce other kind of strange effects. Now, the solution to this problem is implemented in the Weight Watcher project. Weight Watcher is an open source tool. We have over 100,000 downloads, and it is a data-free tool for diagnostics of deep learning models. The way it works is you give it a model. Now, this is some pre-trained model that you have or a model you've trained. Notice you don't need the data, the training data, or the test data. You simply need the model. Weight Watcher looks at each of the individual weight matrices, hence the term Weight Watcher, and it performs spectral analysis or singular value decomposition on the layer weight matrices. It then will plot for you a histogram of the eigenvalues and can give you diagnostic information simply by looking at this histogram. For example, when you first start training a model, the layers will look random-like because you've drawn them from some random weight matrix, and you can fit the layer spectral density, the histogram here, to random matrix theory using this Marchenko-Pasteur model, and you'll see that your eigenvalues follow this nice red curve very cleanly. As you begin to train the model, or models that are trained on simple data sets, you will see spikes appear to the right of this bulk region, which is we call the bulk region, which is fit to the Marchenko-Pasteur random matrix, and you'll see spikes. The spikes are thought to carry the information. This is just like you would see in PCA or other types of information analysis. However, what we have found is in that models that are very well trained for the data sets they're selected for, that is, models that have good out-of-sample performance for their data sets, tend to have weight matrices that have heavy-tailed ESDs. They're heavy-tailed and that they take this nice shape that you can see, but you can also fit the spectral density to a power law. So rho imp of lambda fits to lambda to the minus alpha, where lambda is the eigenvalue and alpha is the power law exponent. And that power law exponent is an example of one of the Weight Watcher layer quality metrics. Let me give you a little more detail of what's going on. If you have Weight Watcher, will analyze the empirical spectral density of the ESD, or the eigenvalues of the layer weight matrices. If we plot this spectral density on a log-log plot, you'll find that it frequently will form a straight line. And we can fit that straight line using a standard MLE estimator to get the slope, which is the power law exponent or the quality metric, and the start of the tail. And the idea is that the tail of the spectral density contains the information that is the generalizing eigencomponents for the layer. And what we would like to show is that as this slope gets smaller, as it reaches 2, that the tail gets larger. There are more eigenvalues in the tail, and you get higher out-of-sample performance, better model quality. Now, the difference between our theory and what many people do in statistics or statistical learning theory is that we are looking at average case behavior, typical behavior, using techniques from statistical mechanics. Therefore, we are interested in the shape of the spectral density. Most models from statistical learning theory or statistics or pack-bounds theory, to take your choice, would look at the scale, or only look at the largest eigenvalue of the model. So what we're doing is subtly but fundamentally different from what's done in statistical learning theory, and you're going to see that there are many things you can learn by looking at the shape of the spectral density. In particular, the spectral density is thought to form a power law, and when it does, or a truncated power law, the exponent alpha will lie between 2 and 6, and you'll get a good quality of fit. For example, the Komalikov-Smirnov distance here is 0.027, the alpha is 3.393 for layer 146 in GPT-2, an old model of GPT. You can do this yourself. You can pip install Weight Watcher, run weightwatcher.analyze, plot equals true. It will generate all of these plots for you, and what you will find is that in models that are well trained, that models that have good out of sample performance for their data sets, most of the layers will be heavy tailed and well shaped and will fit a power law very well. So it turns out the layer alpha is a quality metric that we can use to classify how well a layer has converged. So, for example, if alpha is 6 or more, the layer will be random-like and not contain a lot of information from the data set, and we say that it is underfit. If alpha is 2, then we will show you, and I hope to convince you, that when the alphas are equal to 2, that the layer is ideally fit, and that somehow this layer has captured as efficiently as possible all of the correlations in the data set for that particular view of the data. If alpha is less than 2, it turns out that the layers tend to look like they're overfit, and I'm going to try to argue and present some data that indicates that we can actually detect when a layer is underfit or when a layer is overfit simply by looking at the layer quality metric, but I'm going to show you some other metrics we can look at as well. What can you do with a theory of learning that talks about how the layers converge? Well, one thing I'm frequently asked is, can you speed up neural network training? Can you make it faster? Can you make it cheaper? Well, people don't pay me to train 1,000 layer LLMs, but if you want to, yes, you can speed up the layer. You can accelerate training by adjusting the layer learning rates. That is, in some sense, we have solved the problem of setting the layer learning rates at least toward the end of training. You can accelerate it. How does this work? Well, one, you run Weight Watcher, so you do weight analysis and get the layer-wise power law alpha metric. 2, you then assign a layer-wise learning rate using the temperature balance algorithm. That is, if alpha is overtrained, if alpha is too small, you turn the learning rate down because that layer has learned too much information. It has learned spurious correlations in the data. If alpha is large, it's overtrained, then you need to turn the learning rates up, and therefore you can accelerate training. And we have a paper this year in NeurIPS2023 on temperature balancing, and you can read the paper, and it explains how to use the Weight Watcher tool and the theory here to adjust the layer learning rates, to accelerate training in very, very large models like LLMs. There are other things you can do. For example, let's suppose you're in a company and someone gives you a model and you'd like to know, should I deploy this model in production or is there something wrong with it? One of the things we can do is we can detect presumably quote-unquote bad layers in a model. So we're going to compare here Falcon and Llama, two very popular LLMs. The Falcon models, the 7B and 40B models, are on the left, and the Llama 7B and 65 models are displayed on the right. And what we have here is a histogram of the layer Weight Watcher Quality Metric Alpha. This is the alpha metric for Falcon and Llama. That is a histogram for every layer. These models have hundreds of layers. We compute the layer quality metric alpha for every layer, and we plot a histogram. You can see that for Falcon, most of the alphas lie between 2 and 6. There's no alpha which is smaller than 2, no alpha, only a couple which are greater than 6. That is, Falcon looks like a fairly well-trained model according to our theory. In contrast, if you look at the Llama models, whether you look at 7B or 65B, there are a large number of layers with unusually high alphas. These layers appear to be underfit. And moreover, there appear to be a couple of layers which are overfit, as if the overfit layers are compensating for the underfit layers. Now, why does Falcon look so good, but Llama display these strange anomalies? What we think is going on is that the Llama dataset has too many duplicates. And these duplicates make the dataset look as if it is larger than it is. That is, the Falcon team did a tremendous job of removing duplicates from their dataset. And by removing the duplicates, we feel that the dataset is well sized for the model. And when the model is trained, all the layers converge fairly well. In contrast, we think the Llama team may have had a data set with way too many duplicates in it, and therefore the data set is effectively smaller than they really thought it was. And so when they chose the model size and aligned it with the data set using, say, the chinchilla scaling laws, the data set was too small for the model, and there are a number of layers which simply do not capture enough information. Now, another thing we can do is we believe we can detect which layers may actually be associated with hallucinations. This is some very preliminary work, but let me explain it to you. I took a bunch of models from the Hugging Face leaderboard from a few months ago, and I simply computed the average layer quality metric. I computed alpha for every layer in the model and gave each model an individual quality score. And that quality score ranges between 3 and 4, which is within the range we would like. On the y-axis is the truthfulness QA metric for the base model. And this metric tells you how truthful the model is. Smaller models of the truthfulness means the model hallucinates more. So again, smaller alpha is better. Smaller truthfulness means more hallucinations. It appears that models with smaller alphas tend to have more hallucinations than models with larger alphas. Now, the R squared for this fit is only 0.32, so it's not a great fit, but it does suggest there's something going on in these models, and that models that appear to have converged when the layers have converged better appear to actually are better at lying to you. This, to me, is a pretty amazing result and something we'd like to look into more carefully. So I've given you 3 examples of what you can do with a layer learning theory. What is the theory based on? Well, the theory uses random matrix theory. And the idea is that the more random a layer is, the less information it is absorbed from the model, and therefore it is not converged as well. Here's an example of how random matrix theory works. This is called the Marchenko-Pasteur theory. And the Marchenko-Pasteur random matrix theory says, if your matrix W is a simple Gaussian random matrix, that is, if W is selected from some Gaussian distribution, although this is sufficient but not necessary, then the spectral density will have a very simple known form. That is, this is a sufficient but not necessary condition. There are other conditions which can give a Gaussian random matrix. But the idea is that, given the aspect ratio, the shape, n over m, you'll get the spectral density, the plot of the eigenvalues, will have a very specific form. For example, when Q is 1, when n equals m and the matrix is roughly square, the spectral density will follow this red line. On the other hand, if the matrix is more rectangular, here Q equals 10, the green line, then the spectral density will have this sort of semicircle, distorted semicircle. Now, there are some very key points to note here. Not only does the spectral density follow these lines according only to Q, all you need is the aspect ratio. It also, the edges are very, very crisp, and so you do not expect any bleeding out from the edges. The edges should be very crisp, And when Q is greater than 1, you also see no small eigenvalues, no eigenvalues to the left. So what do we see in reality? Well, in reality, here's a picture of AlexNet FC2. This is the ESD of AlexNet for FC2. Again, I did not train AlexNet. I just pulled it off the internet. I think from Hugging Face or one of these other, and you can plot it, and you'll see that the spectral density follows a nice power law curve, and actually will fit a power law fairly well. The red line corresponds to the predictions from random matrix theory, and you can see that the blue histogram and the red curves are very, very different. It turns out that W is heavy-tailed. Now, how are we going to model W? What we're going to say that if W, the elements of W are heavy-tailed, the elements, then the spectral density will also have heavy tails. However, you also have the case that when the spectral density is heavy tails, if W is strongly correlated, then the ESD can be modeled as if the W elements were drawn from a heavy-tailed distribution. However, we have to be very careful what we mean by that. So what I mean is that sorry, I skipped here. When you look at the spectral density of various kinds of models, AlexNet, VGG, ResNet, DenseNet, BERT, GPT, we've looked at hundreds of models and thousands of layers. All of these layers, if you plot their spectral density, for the most part, 80 to 90% of the layers can be fit to a power law and they exhibit this sort of scale-free behavior. And if you try to fit them to a Marchenko-Pesher distribution, the results don't make any sense. All well-trained modern DNNs tend to exhibit heavy-tailed self-regularization. That is, when the model is well selected for the data and the model has good out-of-sample performance, a high model quality for that data set, you will find that the layers are, the eigenvalues of the layers are heavy-tailed, but the layers themselves, the weight matrix elements themselves, will not be heavy-tailed. This is critical. The weight matrix elements are actually Laplacian distributed, but they're not heavy-tailed. Now, this is critical because there are some people who have presented some theories that show that if you run SGD can give you heavy-tailed elements. And that's fine. We see that as well. But we think that the SGD training is almost a confounder when analyzing the problem, because the elements that come from SGD are spurious and may even correspond to overfitting. And I'm going to make the argument that heavy tails do not solely come from SGD training. And I'm going to do this by looking at a very simple, well-known problem in industry, latent semantic analysis, or LSA. We're going to form the TF-IDF matrix for the 20 news groups, and we're going to compute the empirical spectral density of this TF-IDF matrix. In other words, we're going to look at the SVD on the TF-IDF, and we're going to plot the log eigenvalues, and you see this nice plot. And we're going to fit this plot to a power law distribution, and you'll see that the tail of the distribution starts where this orange-yellow line is. If you then plot the explained variance per component, you would find that the explained variance per component, all the large variances live within the live within the tail of the distribution. That is, the inflection point of this curve corresponds almost perfectly to the start of this power law tail, and the power law alpha exponent is 2.2. This is a very simple model which shows that in a strongly correlated system, you can get a power law, a very nice power law fit with alpha around 2, and yet we have not run SGD at all. So the correlation structure of the model is giving you these power law eigenvalues. It is not necessarily, or probably not even due to the SGD training itself. It's simply that when you train a model, you get a view of the correlations of the data. Now, in our JMLR paper, we present our theory of heavy-tailed self-regularization, and we present a phenomenology. In other words, a bunch of pictures which you can use to sort of qualitatively describe your own model. You can take the Weight Watcher tool, it will generate these plots, it will try to fit the plots to a Marchenko-Pesher distribution, and then you can kind of identify what you feel the weight matrix, what phase the weight matrix is in. And by that what I mean is if we take a model and we start off training it and you plot the spectral density, it will look random and it will fit a Marchenko-Pesher curve. And as the training proceeds, in this case, we trained a model with very, very large batch sizes and systematically decreased them. This is equivalent to training a model with very, very small learning rates and increasing the learning rate. So large batch size corresponds to small learning rates. So when the learning rate is small, you're not learning quite a bit. As you increase the learning rate, you'll begin to see that a few eigenvalues start to pull out to the right side of the bulk region, and they begin to separate, and you get this bulk plus spikes phase. Again, this is what you would see in smaller, older models. It's what you might expect by doing PCA on some simple data set, where there's a clear distinction between the randomized bulk region and the large eigenvalues, which presumably contain the interesting information. But what happens in large modern DNNs, and particularly when you train with small batch sizes or you train with learning rates that are reasonable enough for the thing to converge, that the heavy-tailed nature begins to form. The Marchenko-Pasteur fits are now a really bad model for the system, and you get these heavy tails. And in fact, if you make the batch size really small or the learning rate crazy large, you can actually even get the model to overfit. So what we say is that the DNN training induces a breakdown of the Gaussian random structure from the initial weight matrices and brings on the onset of a type of new heavy-tailed self-regularization. In our paper, we describe the 5+1 phases of training. And again, you have random-like, a bleeding out phase, a bulk plus spikes, you have bulk decay, and you have heavy-tailed. Now, in fact, you can even get a singularity, which means that the system has undergone some form of rank collapse. Now, these phases correspond roughly to what are universality classes that we've discovered from random matrix theory. By discover, I mean that I went into the theoretical physics literature where these ideas were first developed in the 90s, and I sort of looked through and figured out what they discovered. We have a table which explains this. There are the basic universality classes such as the Gaussian Marchenko-Pasteur and the spiked covariance model, which in the physics literature is called the self-organization model. But it turned out there are three or four other universality classes that are indexed by mu, which is a Pareto exponent. Now, rather than go through this, I'm going to explain to you with a simple experiment how you can understand these universality classes. Let us imagine that we have a weight matrix W, and we select the elements Wij from some probability distribution, which is Pareto. So the weight matrix elements are chosen such as X that goes as 1 plus mu, where mu is this Pareto exponent. Now again, in a real deep neural network, Wij are not Pareto. But because of the universality classes and the universality properties of the spectral densities, you can model a strongly correlated system as if you were to draw the elements from a Pareto distribution. So here on the left, I'm going to plot the eigenvalue distribution for these Wij matrices, for these W matrices where I've chosen Wij from a Pareto distribution, where the index of the Pareto parameters 1, 3, and 5, and you can see that as mu gets smaller, the tails get bigger. That is, the tail fills out. We're then going to take this spectral density and use Weight Watcher to fit the alpha power law exponent for these models. And what we find is that the fit depends strongly on the aspect ratio. When mu is less than 2, you'll see that you get roughly a straight line for the aspect ratio of Q equals 1. When the aspect ratios get a little larger, you get this deviation from straight line. But typically theory would say that alpha is 1 plus 1/2 mu. As soon as mu gets larger than 2, you start seeing a shift. Sometimes it's a little hard to see for the larger aspect ratios, but you do see this shift from this straight line to another line. And then as mu approaches 4, you'll see that you start now seeing another shift in the line from this to, you go from very heavy tail to fat tail to weakly heavy tailed. And again, these curves do depend on the aspect ratio. And so it's a little tough to apply this in practice, but we're going to argue that because these systems are strongly correlated, the finite size effects actually aren't as pronounced. But this is what we mean by the universality classes. And again, you can try this yourself. It's fairly easy to reproduce. So we have this notion, and go back here, that when you have a well-trained layer in a model, that is, the model has been well selected for its data and it's trained very well so that the hyperparameters are chosen so that you get really good out-of-sample performance, really good model qualities. You'll find that most of the layers can be fit to a power law. The power law exponent alpha will lie between the range of 2 and 6. roughly, and that the quality of fit is very good. You'll get a nice straight line. Now we're going to present some results that, and moreover, the smaller alpha is, the better the model quality. Now that's a fairly big statement to say that alpha is somehow a measure of the generalization performance of the model. And what I'm going to present to you now is some new results using some ideas from statistical mechanics, which are going to derive this from first principles and show that models that are more heavy-tailed have better generalization performance. So this is called a semi-empirical theory of deep learning, CEDL. This is our current title for the article. Again, myself, Christopher Hendricks, who's been working with me, and Michael Mahoney, who's at UC Berkeley, and has been in the audience today and helped set up our workshop on heavy tails in machine learning and AI. We're going to start with the classic student-teacher model from statistical mechanics. This model dates back to the 80s and 90s, I think the early 90s. And the idea is we're going to model the generalization performance of a multi-layer feed-forward network using a simple vector model of a perceptron. And what you will find, here's a paper by Engel, Theoretical Computer Science. There's some other papers as well, showing some, you'll see the references in our paper. But the idea is that you can predict the generalization error of a model will actually go as 1 minus r, where r is the vector overlap, r dot j dot t, where j is a student and t is a teacher. That is, if you have you have a teacher model, a perceptron vector, and you form a bunch of students which try to mimic or try to learn the labels that the teacher reproduces, standard student-teacher model, you can derive an expression for the generalization error for a linear perceptron in the high temperature limit in the annealed approximation, where the generalization error will go as 1 minus the overlap between the students and the teacher. Moreover, these class of models exhibit phase behavior when they're overfit. Now, you may recognize as complex phase behavior. This is sometimes called double descent. And this sort of was rediscovered. Double descent was first discovered in these student-teacher models. Now, Mike and I have a paper called Rethinking Generalization Requires Revisiting Old Ideas, Statistical Mechanics Approaches and Complex Learning Behavior. This is on the archive from 2017. And we were trying to explain that many of the phenomenon people see in deep learning are actually due to phase behavior. We didn't come up with the fancy term double descent, so the paper hasn't been widely known. But basically what it says is that that these models that all of these neural network models exhibit glacier metastable spin-like phases. That is, if you change the load, or you vary the load, or you vary the temperature, the model can transition from a model that generalizes very well, boom, to a model which has really, really terrible performance. And you can go from perfect performance to really poor performance, or to even have these sort of funny metastable states. And we're going to kind of even show some experiments where we think this is what's going on. But again, this idea of complex phase behavior really comes from theories of statistical mechanics. If you try to do this with statistical learning theory, maybe you can derive it, but the early models never saw this. But this was predicted by statistical mechanics, nearly 30 years ago. Now, what we're going to do is we're going to form a matrix generalized version of the student-teacher model. So, in taking the old student-teacher model, we're going to take the student vectors J, and we're going to generalize them to a weight matrix S, which is an n-by-n real non-symmetric matrix. Now, these matrices are actually, we're not going to postulate S, we're actually going to measure S. So we're going to assume that S forms a heavy-tailed correlation matrix. So A is 1 over n, S transpose S is a heavy-tailed matrix. And that we can model that the student heavy-tailed matrices will actually resemble the heavy-tailed matrices of our model or a teacher, W. And we're going to write the student-teacher matrix overlap as 1 over n S transpose W. So we're going to generalize the idea of a vector overlap with a matrix overlap. And we're going to write down R transpose R as 1 over n W transpose AW. I'm sorry, A actually should be S transpose, but that technical detail doesn't really matter for now. We then are going to write down the free energy associated with the generalization error. The free energy for this is going to be 1 over beta log integral over d mu s, the integral over all possible student weight matrices, times the exponential of minus beta 1 minus 1 over n trace r transpose r to the 1/2. That is, in other words, we're going to take 1 minus r as the generalization error. We're going to write down the free energy for this object, and this is called an Itzakin super free energy because this measure is not a measure over the elements of S, it is a measure over all possible random matrices. This integral can then be reformed into something. This is called an HCIZ integral, which is an integral that arises in theoretical physics, in spin glass theory, and in quantum gravity and other models. The idea is you're going to take the expected value of this integral, where now we have the expected value, just the overlap, the quality. If the error is 1 minus r, then the quality is r, and the quality metric for our layer will be given as beta over 2, where beta is the inverse this free energy, sum over g to the some of these generalized norm functions. And they're generating function. These generating functions depend only on the eigenvalues of the teacher, and they can be written in terms of an R transform. So an R transform is a complex function which can be expanded as a series expansion in terms of the free cumulants. And this generalized norm, or really a norm generating function, can be written down as a simple functional form which you obtain from the empirical eigenvalues. So in other words, we measure the eigenvalues of our model. We plug these eigenvalues into the expression for R, which gives us G, and our Weight Watcher layer quality metric can be written as a log sum over I to m G of A. So we obtain the quality metric from the appropriate derivative of the free energy. But the point here is that, and again, this will all be explained in our technical paper. The point here is that because we have now a theory for the Weight Watcher layer quality metric, which depends on R, and R, these free cumulants are empirical measurables. And what you would find is that if, again, you go back to a model where you have layer ESDs that are heavy-tailed, the more heavy-tailed the layer is, that is, the smaller alpha is, the heavier the tail, the larger are going to be these higher order cumulants, and you're going to get better generalization. And this will occur down to alpha equals 2. So in this, we have, in doing this, we have a theory which gives us an analytic form for a layer quality metric. Now, in order to formulate this theory, we have to introduce some approximations. And one of the approximations is something we can test. It's the idea of a new principle of learning called a volume-preserving transformation. What is this? This principle says that as the layer is ideal, when the ideal layer trained is ideal, then all of the generalizing components, the correlations, will concentrate in the tail of the layer. We call it an effective matrix. And we can perform a change of measure which satisfies a volume-preserving transformation, as we can change the measure from d mu of s to d mu of a. And this measure, to be volume-preserving, states that the determinant of this transformation should be 1. So this sets a condition on the eigenvalues of the tail. If we stick x effective or x into this, we find that the determinant of our effective matrix is 1, or we call this the trace log condition, which is the log of the determinant is approximately 0. And this occurs when, in fact, you normalize things properly. And this is something we can actually test empirically. So I'm going to show you the test. And again, Weight Watcher will actually generate this for you. So here we're going to take this is VGG19 FC1, where alpha is 2.69. We do a power law fit. We do our power law fit, and in doing the fit, we find the start of the tail. The power law tail is lambda min and occurs at this red line. If we apply the condition that the det x is 1, we're basically saying all the eigenvalues in the tail must, when you multiply them up, you get something close to 1. And this purple line corresponds to the closest fit of where we think the tail would start if you use the det x condition. Now, these two conditions are completely independent. The power law fit and this det x condition, this volume-preserving transformation, have nothing to do with each other. And the fact is that we will find that as alpha approaches 2, the det x condition tends to overlap with the start of the tail. So the way we have been defining our tails using the power law fits actually correspond directly to what our theoretical results suggest. Now here are some examples. We're going to look, this delta lambda min is the difference between this purple and red line. And what we're going to find if we look at various models like the VGG series or the ResNet series, and we fit the power law alpha, and we compute this delta lambda min. I'm sorry, got cut off here. We see that as alpha approaches 2, this delta lambda approaches 0. And in fact, when alpha is less than 2, it can even be smaller than 0. So, and we see this happens in the VGG series, in the ResNet series. Here's Falcon, here's Llama. It's almost as if there's a funnel that as the alphas tend to systematically get smaller, this delta lambda volume preserving condition tends to work better and better. So based on these experiments, we think that we have discovered a new principle of learning, which suggests that as a layer alpha approaches 2, as the power law fit gets better and better and approaches this ideal value of 2, that the start of the power law fit corresponds exactly to the case where the tail defines a volume preserving transformation between the weight matrix and its correlations. Now here's some more proof, another empirical example. We have taken, again, this will all be in our new paper, Seidel, Semi-Empirical Theory of Deep Learning. We take a 3-layer MLP and we train it on mints and we vary the learning rate. And we try to get the best model we can by doing this, training it for a long period, training it to a certain point. But we then we compute the train error minus the truncated train error. So what we're going to do here is we're going to take the first layer, FC1 of our model, and we're going to run truncated SVD, where all we do is keep the SVD defined by either the power law tail or this dead X condition. And what you find is that when we train the truncated SVD minus the training error, as the alpha approaches 2, the difference between the truncated training error and the training error is blue. The difference between the truncated test error and the real test error is orange. And we can see that the orange actually approaches 0. So in other words, the generalizing components appear to concentrate in the SVD truncated tail of this layer. Notice that the training error, there's always a little bit of a difference. So we don't reproduce the training error exactly, but we can reproduce test errors exactly by doing truncated SVD. In comparison, this train minus test error is the generalization gap. And so, again, we're not concerned with the generalization gap, which a lot of people are concerned. We're concerned with the train minus test error. So this is somewhat remarkable. And what we believe is that we've discovered a new principle of learning, and a principle which tells us what does it mean for a layer to be ideally trained. And that tends to correspond to alpha being equal to 2 and the dead X condition, the volume transformation, the volume preserving transformation holds. Now, since we seem to have identified alpha equals 2 as an ideal condition, we wonder what happens when alpha is less than 2. So here we're going to see whether we can detect overfitting. And again, we're going to try to detect overfitting in a model without ever looking at the test data. So here we take, again, our MLP3, and we are trained on MNIST, and we vary the learning rate, and we train it to try to get the smallest error we can. And we see that as we increase the learning rate, the error decreases, and all of a sudden it goes up. So as we decrease the learning rate from 1 to 4, 8, 16 seems to be about the best learning rate. When we double it, the learning rate, we see there's the learning rate goes up, the error goes up. If we look at alpha, again on this layer, we find that as we increase the learning rate, alpha decreases, and all of a sudden when the learning rate gets too large, bam, alpha drops right below 2. This is actually predicted by other theories that say that if you have the learning rate too large, you can induce anomalies in the weight matrix, which make the elements of the weight matrix appear to be more heavy-tailed. And when we do this, this is what we will see. If we take this model of, we take this layer in particular. Now I'm showing you an idealized case, but in our paper we actually do have this. You'll see that when you have a layer that is well trained, it follows us. If we plot the log eigenvalues in green, they look heavy-tailed. And it's not perfect. There's some maybe a little distortion, but it's heavy-tailed. If you were to randomize the elements of W and plot their eigenvalues, it would fit this Marchenko-Bashir random matrix theory perfectly. If, however, you see what we call a correlation trap, that is when we train a model with a spuriously large learning rate, you can see that you take the eigenvalues of if you randomize the weight matrix and compute its eigenvalues, frequently you'll see this orange line being a large eigenvalue pulling out from the bulk, which corresponds to a rank 1 perturbation in the model. So what we believe is happening is that you get these sort of funny rank 1 perturbations when the learning rates are large, or other funny things happen, and we think that these may be associated with some form of overfitting. Now, we don't fully understand this phenomenon, but we call these correlation traps, because we think what can happen sometimes is that it will distort the actual spectral density. So instead of seeing a nice clean power law, you get sort of this funny bump at the end, and so we think that what's happening here is that somehow either large learning rates or other odd phenomenon in SGD training can induce perturbations in the actual W matrix itself and the elements, which may be corresponding to decreased generalization performance. Now, finally, we're going to try another experiment where we try to detect overfitting by reducing the capacity of the model. So we're going to try to mimic this thing we saw in Llama, where there are layers that tend to be random. So what we're going to do is we're going to train our MLP3 on Menst, but we're going to reduce the capacity of the model by freezing the layers. So, for example, we'll freeze FC2 and FC3 to be random and just train FC1. Now, FC1 is a fairly large layer for this model, and it dominates. So when you do this and you train with different learning rates and you compute the training error, the learning rate doesn't, versus alpha, you see that the alphas just sort of systematically go down, and then they start to decrease slowly, basically as you're approaching, the error approaches 0. But if you look at the test error, amazingly, as soon as you see this nice smooth curve when we train the model with FC1, and the test error decreases, but as soon as you hit alpha equals 2, the decrease in the test error slows down. The dynamics of the model slows down. And we think this is an example of a model being somewhat in a glassy state. By the way, these test errors are somewhat large. Recall, if you go back to this plot, you'll see that a good test error is around 0.17. These test errors, you can see, are way up above. The good test error is down here, in this region. The model never recovers the perfect test error. It sort of saturates way above what it should be for this data set. But you see this sort of slowing down in the dynamics, which we argue is a type of glassy or metastable behavior. And we have several examples of this, which we're going to point out in the paper. Now, I'm going to take a stop and sort of explain something interesting that people may not know about if you don't know about neuroscience. When I was a postdoctoral student in deep learning and neural networks, we had part of our group doing experimental neuroscience. And one of the things that we would do is we would look at spiking. We'd take cultured neurons and look at their spiking activity. Because, real-world neurons tend to send electrical signals to each other. And, and what we find is that if you look over time, you will see that these neurons exhibit avalanches behavior. That is, they will tend to not spike for a while, and then they all start spiking at once and they stop. Then they won't spike for a while, and they all start spiking at once and they stop. And this is called an avalanche. And if you fit the size of these avalanches, what you would find is the size of these spike patterns exhibit power law behavior. That is, these spatial distributions tend to fit a power law, and sometimes the power law sort of goes down, or sometimes it goes to the right. Sort of there are some finite size effects, but for the most part, you see power law in these spikes. And this is called the critical brain hypothesis, and it's evidence of self-organized criticality. So this was predicted by a fellow named Bach back in my time, a late physicist, who predicted this idea that actual systems can undergo, like these spiking neurons will undergo a form of self-organized criticality, and that they will exhibit power law behavior. That is, if you look at the structure of the correlations, they will exhibit, the size of the correlations appear to exhibit, or it can be well fit to power laws. And as neural systems become more complex, they exhibit power law behavior. And as they become very complex, they exhibit truncated power law behavior. Now, we see the exact same behavior in DNNs. And in fact, it appears to be predictive of their learning capacity. And it was this this idea that really motivated a lot of the early work when we started Weight Watcher to see, could we see these signatures of self-organized criticality, that is power signatures, in real-world systems. And what we found is that you look at bigger and bigger models like the Falcon models and the Blue models, they actually do exhibit this. Now finally, I'd like to just stop and say this work is all implemented in the Weight Watcher project. You can go to https://weightwatcher.ai. You can learn about Weight Watcher. Weight Watcher is a diagnostic tool. It's a data-free diagnostic tool for deep learning. As I said, it's a one-of-a-kind tool for anyone training, deploying, or monitoring deep neural networks. It's all open source. Pip install Weight Watcher. We have, when I did this, we had 104. I think we have 125,000 downloads by now, maybe 115,000, over 1,000 stars on GitHub, and we are looking for early adopters and collaborators to work with this project. Please reach out to me because we have both the open source version and a working enterprise version, and we'd love to work with you if you are fine-tuning or training your own LLMs, you're just having trouble evaluating them. Please reach out. Thank you again. And that concludes our talk.